So welcome to everybody. We are here to attend Mrs. Valeria Cerqui PhD defense. Valeria prepared her thesis here in l'Observatoire de Paris, Paris-Sciences et Lettres University, in GP, in the group Étoiles et des Galaxies, under the supervision of Michel. Our thesis subject is the evolution of the galactic disk in a new era of galactic archaeology. So the thesis jury is composed of 6 members, 2 referees, Professor Thomas Bensby from Lund Observatory, Sweden, Professor Andrea Miglio from University of Bologna, Italy, Dr. Georges Cordopatis, HDR, from the Lagrange Laboratory Observatoire de la Computation, and in visio conference, Professor Céline Rayet from Institut Huguenal in Besançon Observatory, and finally Michel Wood, as a supervisor, and myself, Yveline Breton, astronomer at the Observatoire de Paris and the PSL University. So formally, we have to decide now who will be the president of the jury. And so traditionally, it's a member of the PSL University. So if the jury agrees, I will take that role. Okay. So first of yes, sorry. So both reviewers have approved the defense. So Valeria, we will now listen to your presentation, which should take about 45-50 minutes. And then we will have some questions and deliberation. Yes. So please take the floor.
Good morning to everyone, and thanks to be here. I'm really happy to be here and to show the results of my PhD. And in particular, as Lynn said, I will talk about the chemical evolution of the galactic disk in a new era of galactic archaeology. I would like to start with this movie because it's a cosmological simulation from Wintergatan. And this is a nice example of how a disk in a galaxy like the Milky Way formed during time. In particular, this simulation is tracing the gas density during the time. You can appreciate the morphology this is evolving, the formation of the disk, the spiral arms, the formation of a central bar, but you can also appreciate that the galaxy is accreting gas from both filaments and also from small and massive satellites. This is just an example to show how a disk in a galaxy is the result of a complex interplay between internal and external mechanisms. And it's a challenge to reconstruct all these mechanisms from what we see nowadays, so the stellar population of disks. Indeed, I show you the gas, but from the gas form stars, and all the processes and mechanisms that take place to form a disk are imprinted in the stellar population of the galactic disk. This is a picture of the Milky Way from Gaia Year 2, and we started understanding 40 years ago that the Milky Way disk is not a simple disk, but is made at least of 2 components called thin and thick disks. They differ from each other from a number of properties, and starting from morphology, the thick disk is dominant in the inner part of the galaxy up to the solar neighborhood, while the thin disk extends at least 20 kpc from the galactic center. On the other hand, the thick disk scale gate is 3 times higher than the one of the thin disk. In addition to that, they also differ from kinematic properties. To highlight this, I show this two-ray diagram taken from Lagarde 2021, where on the x-axis we have the rotation of the stars, on the y-axis we have a combination of radial and vertical velocity. The thin disk stars in the solar neighborhood rotate with a velocity consistent with the velocity of the galaxy, 220 kilometers per second, and spans a small range of radial and vertical velocity. On the other hand, the thick disk stars in the solar neighborhood rotate with velocities lower than that and spans a larger range of vertical velocity and radial velocity. And this is why we call them thick disk this is why we call we say that these stars have hot kinematics. In addition to that, they also differ from chemistry. And I show an example here of age alpha over iron relation from a solar neighborhood star taken from Haywood 2015. You can clearly see that we have two sequences in display. The first is the thick disk or high alpha sequence made from all the stars and alpha element enhanced, while the thin disk sequence here spans a younger and wider range in age. The statement here is that the older stars in the galactic disk have higher values of alpha over iron and that are found at higher distances from the galactic plane. And this is why we call them thick disk stars. All these properties are not only properties of the Milky Way, but are also observed in other external galaxies. For example, if you look at the left plot, you will see a slice of a disk of this external galaxy. So in the x-axis, we have the distance from the galactic center. On the y-axis, we have the distance from the mid-plane of the galaxy. And you will find that the stars that are the most distant from the galactic mid-plane are the oldest one, the metal poorer and the alpha enhanced stars, like in the Milky Way. And this is just an example to show that it's important to reconstruct the properties of the Milky Way because they can tell something also of the other galaxy, about the other galaxies. In this context, the goal of my thesis is to reconstruct the chemical evolutionary history of the galactic disk using information that are fossilized in the stars, like chemical abundances, and it's link them with stellar ages. Once we have the chemical evolution of the galaxy, we can infer then constraints on also the gas accretion and the star formation history of the Milky Way itself, because these three properties are strictly correlated to each other. Here I give you an outline of the talk that I'm going to give. First, I will show the data that I used during my thesis. Then I will present the first results concerning a peculiar type of stars called young alpha-rich stars. Then I will highlight the main results of my thesis about the chemical evolution of the disk, and I will end to show how some dynamical processes in the galaxy contribute to shape this chemical evolution. And then I conclude and we show some perspective of the work. So starting with the data, I want to introduce you a survey that is really leading the role in galactic archaeology, that is the space mission Gaia, that has the aim of reconstruct the 3D spatial and velocity distributions of stars to map the formation and evolution of the galaxy. And with the latest data release 3, not only fulfills the goal, but also provide the most accurate position, parallaxes, and proper motion ever produced in the optical range for more than 1 billion of Milky Way stars. But not only, because in addition to that, it also provides very precise photometry in 3-band thèse and radial velocities. Another important service nowadays for galactic archaeology is Apogee, that has the aim of mapping the chemodynamics of the structural components of the Milky Way. In particular, it is a ground-based near-infrared spectroscopic survey that provides atmospheric parameters and abundances for 20 chemical elements over 700 stars across the Milky Way. And it's very helpful because operating in the near infrared, it can reach the dust obscure the regions of the Milky Way, like the central region and the disk. In particular, I also used a lot during my PhD the value-added catalog AstroNN of Apogee, especially for ages that are calibrated on asteroseismology and distances and orbital parameters. So the synergy between these two surveys is really ideal to achieving the goal of my research, and this is why I use them a lot during these years. So I will start talking about young alpha-rich stars, peculiar type of stars in the galactic disk. And these results are contained in a paper that was published last year. So one of the first discoveries of young alpha-rich stars can be attributed to the works made by Fuhrman. In particular, he found peculiar stars, HR3138. It is peculiar because it was chemically identified like a null-thick disk stars, because it's relying in the high alpha sequence in this chemical plane, and usually the stars, as I said before, of the belonging to the thick disk are older than 8-9 gigayear. But when the authors went to date these stars with evolutionary tracks, they found the stars being young as 6 gigayear. And to explain this peculiarity, they proposed that a mass transfer scenario could explain these properties, adding some mass to the stars, and so the stars really appearing younger than what really was. In the last decade, then, large spectroscopic surveys and the advent of new, more precise age determination have provided a way to increase the size of the young alpha-rich samples, locating them as outliers of the age alpha distribution of the galactic disk. Indeed, they locate here where they are alpha-enhanced and younger than usually 7, 6 gigayear, depends. And in a region that usually is not explained by standard galactic chemical evolution. So far, there have been proposed two possible scenarios to explain the existence of these stars. The first sees these stars as intrinsically young, forming isolated part of the interstellar medium in the inner disk, and then spreading the disk by radial migration. While in opposition, the second scenarios really think about the stars as intrinsically old, part of the thick disk population that only appear young because of mass transfers on multiple systems that they undergone through. This is last scenario is reminiscent of what been proposed for blue straggler stars, that are peculiar stars found in globular clusters, being more luminous and located to the left upper part of the main sequence turn-off of a globular cluster. So a way to investigate the origin of these stars is really to compare the properties of a young alpha-rich sample to the properties of a thick disk reference population in order to see if these properties match and if this population then are the same. This is what I've done, starting from red giant stars of Apogee, and I selected the giant stars because they span a wider range in radius from the galactic center, and so they allow to study the young alpha-rich stars across the whole disk. I've then selected a thick disk reference population in this alpha over iron versus metallicity plane with this cut made by eye. And I finally selected my sample of young alpha-rich stars, where they are located as outliers, as I said, of the age-alpha relation. In particular, the age is taken, as I said also before, from AstroNN. And in particular, selected them to be younger than 4 gig a year and having an alpha Orarum content above 0.15 depth. With this selection, I ended up with 250 young alpha-rich stars, and you can appreciate that the number of young alpha-rich stars increase while going in the inner disk, as is expected from an exponential density law. So as I said, I compared the properties of these two samples, and overall I found that young alpha-rich stars have the same similar, let's say, metallicity and alpha abundance distribution of the thick disk reference population. And you can appreciate this from the metallicity distribution function, the alpha distribution function, but also from the alpha Orarum versus metallicity plane, where the thick disks are represented by the isodensity contours and the young alpha-rich stars are the points in black. In addition to that, they also have the same kinematics of the thick disk reference population, and you can appreciate this from this two-meter diagram. And these results are all in agreement with other results found in the literature. Then we wanted to investigate the position of the young alpha-rich stars in the HR diagram. Here I plot in gray the thick disk reference population, while the young alpha-rich stars are color-coded by their ages. You can see that the young alpha-rich stars are located to the left part of the background, let's say, sequence of the background distribution, as it's expected from an evolution of more massive stars, and also that within the young alpha-rich sequence, the most massive objects traced by their very young ages are hotter than the least massive ones. And to investigate this hint of more massive stars more, we also looked at the mass distribution of these two samples, in particular relying on mass from a star horse that is providing not only masses but other stellar parameters for different surveys, not only apogee. The thick disk reference population have a peak in mass at about 0.9 solar masses, while the young alpha-rich stars have a tail that extends to really more massive values. But young alpha-rich stars are not only restricted to giants. Indeed, if we extend our young alpha-rich selection criteria to the whole apogee dataset, we end up with a number of blue straggler stars, as the stars that I mentioned before in the introduction. And therefore, large spectroscopic surveys provide the opportunity to extend the mapping of the blue stragglers to all stellar evolutionary masses. And also you can appreciate that these stars are more massive than the thick disk reference population. So this first analysis point to the fact that young alpha-rich stars are part of the thick disk population, and therefore they must have been undergone through a mass acquisition event that make them appear younger. And at this point, we wanted to investigate more about the origin of this mass acquisition, and we relied on chemical abundances. Indeed, for example, if a young alpha-rich star is a product of a collision or coalescence between two or more stars, it has been proposed by models that the final chemical profile of this product is very similar to the one of the parent stars. On the other hand, if the young alpha-rich stars are expected to form through mass transfer from a companion, models show that we should expect a surface contamination by elements that are typical of the evolutionary stage of the donor. With this in mind, we investigated the different distribution of particular elements, and in particular of cerium and sodium. Cerium, because it's a neutron capture element that is created in the latest stage of stellar evolution in HGB stars. And therefore, if we found a variation in the cerium profile of the stars, this could be an hint of a mass transfer between an HGB stars and a companion. We found that young alpha-rich stars are more cerium enhanced of 0.15 dec, more or less, in respect to the thick disk reference population. This is a trend that is also confirmed by the Bablas catalog that gives a nice comparison, also in terms of comparisons to this data, and therefore we really believe that this signature is real. We also investigated the sodium profile because it has been suggested by model that mixing in stars can modify the sodium abundances depending on the mass of the stars. We find young alpha-rich stars being more sodium enhanced, about 0.2 dec, and that in respect to the thick disk, and that this enhancement is this shift in the distribution is mainly due to stars, young alpha-rich stars, more massive than 1.2 solar masses. And this is, for example, what have been proposed by the models taking into account the rotation of the stars, like the one of Lagarde 2012. To conclude, young alpha-rich stars are rejuvenated stars by a mass acquisition event. Max transfer in our case can explain the variation in the sodium and cerium profile of most of our young alpha-rich stars, while the collision scenarios could produce the most massive stragglers that we found in our sample. I will now move to the main results of my thesis, talking about the chemical evolution of the disk with a more general approach than what I've shown just now. And these results are in a paper that was submitted in October to ANA, and another one that is also in preparation. So as I said in the introduction, the variation in the production of chemical elements with time and their dilution in interstellar medium depends strongly on both star formation rate and gas accretion rate. And for this reason, they provide strong constraints on the evolution of our galaxy. However, these constraints can be difficult to interpret because these variations are also function of the position in the galaxy, and also because of dynamical mechanisms that can take place and redistribute stars around the disk. With this in mind, we investigated the variation of chemical elements with age in a sample of local vicinity stars with two main questions in mind. First, which kind of structure we can identify in the age chemistry relation in the local neighborhood. And second, if these structures are only the product of a local chemical evolution or they are linked to the evolution outside the solar vicinity. So to fulfill this purpose, I investigated a sample of dwarf stars from GTR 17 and that are located within 2 kpc from the Sun. And after some flex selection, some quality selection, and after having cleaned the sample from binary stars, we ended up with 30,000 solar vicinity dwarfs. I show the sample here in this color magnitude diagram, color-coded by the metallicity of the stars, while in gray we have the background apogee stars within 2 kpc from the Sun. This color magnitude diagram was obtained with the Gaia DR3 magnitudes and color, Gaia DR3 parallaxes, and the magnitudes were also corrected by the effect of the extinction using extinction map from Vermont 2019. In order to reconstruct age chemistry relation, we need age determination. And we relied in a method, a Bayesian inference method, based on Jorgensen and Lindgren 2005. It allows to determine stellar ages and their uncertainties from observational data and theoretical isochrones that describe the evolution of a stellar model in the color magnitude diagram. Up After some tests, we decided to utilize guided photometry as input parameters for our age determination, together with the metallicity of the stars and the alpha content of the stars. And for the model, we relied on the young-scale isochrons. This method allowed to reconstruct for each stars relative posterior probability density as function of the age, or the so-called PDF. From the PDF, then we can derive the most probable age and the Gaussian uncertainties. In particular, we take the value of the age as the maximum of the PDF. The advantages of this method, in respect also to a more simple isochron fitting method, is to quantify the statistical reliability of the determined ages as a function of the observational uncertainties. In addition, it allows to take into account stellar or galactic priors that acts like a sort of weight in the probability of a star. And in our case, we utilize the Fred priors for aging metallicity and a group IMF for the mass distribution. When we rely on stellar isochrons to determine ages, one thing that needs to be done is to pass from the theoretical plane of the isochrons, luminosity and effective temperature, usually, from the observational plane of the data. We did that using volumetric correction from Casagrande and Vandenberg to convert luminosity to magnitudes, and we perform our own calibration to convert effective temperature to pulses. This is the final sample color-coded by the age. So now that we have the age, we really can study the age alpha and age metallicity relation across the disk, and to reconstruct, we can reconstruct the evolution, chemical evolution of the disk. I show here the age alpha relation and the age metallicity relation on the right for 3 different levels of age uncertainties. Overall, we can appreciate that the spread in age at a given metallicity or alpha abundance decreases when the uncertainties of the age decreases, as it is expected. And then in general, in all the relation, we can see clean structures, let's say. In particular, we really can appreciate a really defined and tight correlation for the thick disk, both in the age alpha and the age metallicity relation, that is separated in terms of slope of the relation from the thin disk sequence at 8 gigayear. In particular, you can see that the metallicity dispersion in the age metallicity relation is really increasing from 0.2 dec, more or less, at 8 gigayear to 1 dec in metallicity at any given age below 8 gigayear. In a plane like this, in a scatter plot, we were not able to really identify some structure, especially in the thin disk. So we utilized the 2 density histograms that reveals clear features, in particular for the thin disk. The 3 main features of this age metallicity relation are that we have a clean thick disk relation, taking the stars, the oldest and metal poorest stars of our sample, at 12 gigayear, up to solar metallicity at about 7-8 gigayear. Then we have a decreasing metallicity from 7 to 5 gigayear, down to minus 0.1 dec. And finally, we can appreciate that stars younger than 5 gigayear form a clump at metallicity above solar. Now that we characterized the main properties of this age alpha relation, age metallicity relation in the solar neighborhood, we really wanted to see if these features varied along the disk, so in different regions of the disk. To do so, we divided the sample range of guiding radius that approximates the mean radius of the orbit of a star, defining an inner region, an intermediate disk, and an outer disk. The age metallicity relation in the inner disk show a really defined disk, a sequence up to 7-8 gigayear, and the younger inner thin disk that forms a sort of clump at ages younger than 5 gigayear, let's say. The local intermediate disk age metallicity relation shows still a thick disk sequence that is less defined because it's less populated, the thick disk in this region. And then the signatures, let's say that this metallicity decrease of signature appears as the signature that I showed before in the general relation. In the outer disk, we can see that there is basically no thick disk. It's restricted to low alpha stars. That the outer disk is characterized by lower metallicity in respect to the inner disk, and that okay, we have a spread in metallicity here because of the selection that we have made. In order to really understand these properties, we relied on a chemical evolution model that Owens, Nate and collaborators built first in 2014, and that it has these stellar hits, IMF, and supernova type 1a time delay distribution. In particular, Snate and collaborators used this model first in 2015 to model local stars in a closed box mode where the gas reservoir is in place since the beginning, and then in 2022 in a sort of open box mode that allows gas infall and a sweet chemical flow. We used the model for the inner disk region as in a closed box mode. So as I said, all the gas is in place since the beginning and no inflow or outflow activity. In particular, we fit this model into the age alpha relation of the inner disk stars. Because why the age alpha relation? Because the alpha over iron content its variation in particular through time is really dependent on the level of the star formation rate at that time, and therefore usually higher the decrease in alpha over iron in a range of time, higher will be the star formation rate that caused this decrease. So with this fitting, we end up with a star formation history that show an intense star formation between 8 and 12 gigayear, with the most of the stellar mass that forms in the first 3 gigayears of evolution. When we now look at the local disk, we'll actually not fit them. We didn't fit the model in the data, but we wanted just to show that a simple modification from the model using the closed box mode can really reproduce the main features of the age metallicity in the intermediate disk. In particular, closed box can really reproduce the monotonic increase in metallicity up to 8 gigayear on the thick disk. And then we added a dilution at 7.2 gigayear over a period of 2 billion years to reproduce the decrease in metallicity. For the outer disk, we added more dilution gradually at 9.2 gigayear, each 2 gigayear, a step of 2 gigayear, and it allows to really reproduce the slow variation of iron over age over the time, if you look at the really most metal poor stars of the sample. To validate all these features, all these results that we found, we also looked at giant stars in apogee to really look outward also along the entire disk and not being restricted only to giants. Be careful that now the ages are taken from the AstroNet, so the age scales between these two samples are different. So here I show the plot, in this plot, the models that are reproduced in the used to reproduce the main features found in dwarfs, while the underlying distribution is the distribution of giant stars. In general, models qualitatively are in agreement with the data in the three regions, inner, intermediate, and outer disk, but there are some differences. In particular, if you look at the intermediate disk age-metallicity relation, we can see that there is a lack of metallicity decrease in the giant stars at ages below 7 gigayear, and this is possibly due to the age scales of asteroid N. While if you look in the inner disk, you can see that there are some systematic offset. For example, if you look at the thick disk sequence that reproduce the dwarfs and that reproduce the giants, you will see that the models is systematically older than the distribution of the giant stars. But also that we have, looking at the thin disk sequence, a systematic offset also in alpha over iron. I will now summarize a main scenario that can explain put together all these evidences that we found. In order to justify formation of a massive disk in the inner disk, we need an early massive gas accretion that trigger a high level of star formation and that produce a rapid chemical enrichment in the first 3 gigayear of formation. And then the evolution of the inner thin disk can be explained without relying in any additional gas inflows or outflows. The evolution of the outer disk is independent from the possible enrichment in the interstellar medium of the inner thick disk. The metallicity is lower in respect to the inner thin disk, and it remains lower over time. This is because the outer disk is a low density region, also characterized by a low density star formation efficiency, low star formation efficiency. At the end, the intermediate disk inherits the chemistry of the inner thick disk, in the sense that the thick disk pollutes the local region and can explain the solar metallicity that we have at 8 gigayear in the local region. But it also, the local disk also experiences a moderate dilution from a gas from the outer disk. These new results bring two main evidences. The first is that we have 3 different regimes of chemical evolution in 3 different regions of our galaxy: the inner, the intermediate, and the outer disk. And then that we have evidence of gas dilution that occurred 7-8 gigayear ago in the local dwarf data. I will now end the part of the results of the talk talking about the role of dynamical processes that can shape the evolution of the chemical evolution of the disk, and in particular I will talk about the galactic bar. Indeed, the Milky Way contains a massive stellar bar in the central region that rotates around the galactic center with a pattern speed that is estimated to be about 35 kilometers per second. This rotation of the bar implies the presence of dynamical resonances in the disk. And in particular, the 2 main resonances in the disk are the co-rotation, where the stars orbit around the galaxy with the same angular velocity of the bar pattern speed, and then the outer limblad resonance, or OLR, where the stars complete 2 radial oscillations in 1 revolution around the bar. Therefore, the location of the resonances depends on the bar pattern speed, and new results, recent results, locate the co-rotation and the OLR in the disk at about 7, 11, and 12 kpc respectively. I gave you the number of the bar pattern speed, but the numerical simulation show that the bar pattern speed in this galaxy generally change with time and decrease with time, especially in the first 1 to 2 billion years after its formation. This implies that the resonances in the disk move outwards when the bars slow down. As you can see in this sketch, where we have the first the time zero, the position of the co-rotation and ULR, and when the bar slows down, you can see that the co-rotation and ULR move outwards. And then stars that are trapped at the resonances move outwards with them. We ask ourselves in this project if we could find signatures of this band slowing down in the chemical structure of the disk. And we analyzed an n-body hydrodynamical simulation coupled with chemical evolution for a Milky Way-like galaxy. And in particular, we investigated this metallicity guiding radius plane. In particular, this plane is important because, as I said also before in the talk, metallicity is different in the inner and the outer disk. And so it can really be used as a proxy of the stellar burst radii. We can see in this plot that we have two regimes, let's say, stars older than 7-9 gigayear presents this knee-like feature and also this that produce this also vertical distribution, let's say, that happen to be at the radius of the at the co-rotation of the ULR in the disk in the simulation. And this feature can be interpreted as the bar slowing down that produces a significant migration of inner disk stars that in our simulation are metal-rich stars and up to the ULR and induce then this knee in the first 3 gigayear of evolution of the galaxy. Then in the last 7 gigayear, the bar pattern space does not change significantly, so you don't have migration from stars in the inner disk, and these two quantities are show a better correlation. So the slowdown of the bar is really imprinted as a knee or step-like features in the metallicity guiding radius plane. At this point, it was interesting to go and see what we see in the data. In particular, we looked at giant stars in apogee astro N, and we found signature of the same knee features for stars older than 5-7 gigayear. Given that we find these signatures in the data, and given also that in the simulation, the slowing down of the bar is happening 1-2 gigayear after the bar formation, we can put the constraints on the formation of the galactic bar and say that it formed about 8-10 gigayear ago. But the other interesting result is that the knee-like feature that we observe in the data is really happening at the OLR position in the disk nowadays. And therefore, this is a really signatures of the fact that the metallicity profile of the disk is shaped by the resonances of the bar. And to show you this even more, I show the main metallicity profile of the low alpha disk in apogee DR17 red giant stars. You can see that it's a structure metallicity profiles and that it changes slopes where the co-rotation and ULR are located. And this really is saying to us that the bar co-rotation and ULR divide the galactic disk in 3 segments, but not only, that have contributed in defining these 3 disks in different regions of chemical evolution that I showed you before. I will now conclude. So in the first part of the talk, I highlight to you how in different kind of processes involved in the formation of disks in galaxies leave imprints on their stellar populations. In particular, in our Milky Way, but not only, these mechanisms shape the disk in a thin and thin disk components that differ from each other from a number of properties. The goal of my thesis was to investigate more these properties using the chemistry of the star and its link with the stellar ages to recover the overall clinical evolution of the galactic disk. In particular, the age alpha over iron plane was really helpful into locating a peculiar type of stars, young alpha-rich stars, as outliers of the main distribution of the galactic disk in this plane. In particular, young alpha-rich stars are alpha element enhanced and younger than the typical thick disk population. And our analysis proved that these young alpha-rich stars are part of the thick disk and that they are intrinsically old and rejuvenated from a mass acquisition event. In particular, mass transfer from a star, a companion, can explain the variation of cerium and sodium in the profile of the young alpha-rich stars, and collision scenario can reproduce the most massive stragglers in our sample. I then moved to explain more generally the chemical evolution of the galactic disk using a sample of dwarf stars in apogee GDR17. And I studied the age chemistry relation of this sample along 3 different ranges in guiding radius. And my findings are that there are 3 different regimes of chemical evolution for 3 different regions in the Milky Way, and that also the age metallicity relation of dwarf stars shows a signature of a dilution event that happened in the local region at 7 gigayear ago, more or less. I will then highlight to you how the galactic bar may be contributed in defining these 3 regions of chemical evolution. But not only, I also show you how from the chemical structure of the disk, in particular from the metallicity profile of the disk, we can constrain something about the formation of the bar. Looking ahead, new future releases of Gaia and the combination with the upcoming spectroscopic surveys like Foremost Weave Moons and DSS-5 will allow a deeper study of chemical abundances and kinematics across the galactic disk. In particular, for sure, stellar ages will be improved significantly, we hope, from this amount of data. Not only the age resolution and the uncertainties of the age, but also we hope to have an absolute age scale that will allow to get rid of the uncertainties that characterize the first phases of the galactic disk, formation of the galactic disk. Another topic that could benefit from this wealth of data is the real role of the galactic bar in shaping the synergy disk, not only to shaping the chemical profile as I showed you before, but real if it plays a role between the transition of these 2 components. Thank you for your attention.
Thank you very much, Valeria. So we will now change the questions. Thomas, please.
Okay. Thank you, Valeria, for a very nice presentation, and I enjoyed reading the thesis. I learned a lot, I think. So I have a few questions.
Yes.
So to start with, I tried to figure out which order to take this question, but I think I just so these young alpha-rich stars, they are chemically as thick disk stars, almost, right? Because you say that there is a slight shift in
some elements.
Some elements. So is this real, or could it be because of something else?
Well, actually, this shift that we found is really small between the distribution, and maybe it could also be due to some size systematics, but it needs to be maybe investigated more with also a more enlarged data set. But for example, for some elements like cerium, as I said, we are almost confident that this feature is real because we saw it also in the Pavlas catalog, that is a catalog that provides chemical elements for apogee stars that are really catalog like really a bit difficult, let's say, to derive in apogee, like the cilium element. And also we checked also in the AstroNN abundances that they confirm this shift. So we think that it's real, and that could be due to the mass transfer from an AGB star.
So I assume that in order to say something about the distributions of the thick disk in terms of abundances, ages, whatever kind of distribution, you should also then, I mean, you usually try to select thick disk stars, but then you also have, you say, 7 to 10% of the thick disk is in the straggler or these.
Yeah.
So then you should also transfer those stars into, which could be.
So what do you mean with that?
You need to include them in when you're trying to characterize the thick disk.
Okay, yes. But we decided to focus only on a particular, let's say, stellar type because when I went to see the age alpha or age metallicity distribution of red clamp, red giants, and dwarfs in apogee, we see that there are some shifting abundances between the different stellar types in the same survey. So we wanted to, since we selected by eye also from the chemical plane, we wanted to be sure that there were not like variation induced by this.
So I assume there are also blue stragglers in the thin disk.
But okay.
So, but they might not be as easily identified because if they are moving in age, I mean, and the thin disk is already flat in some sense. So if you were to plot them, but how would that? I don't know. I mean, I don't know much about about blue stragglers, but I was just thinking how they could possibly affect the metallicity distribution or the age distribution that we observe for the thin disk, because they might appear then younger than what they actually are.
Well, yes, but the younger, let's say the stars that we found, the stragglers that we found, are really at the same kinematics, similar kinematics of the thick disk. So we don't find it in the same disk.
Okay.
Well,
okay, thanks. I was looking at a figure that you had in your thesis on page 92. I don't know. I don't know if you showed it here or not. But
about what?
It was. So you showed it was on chapter 4.
Yeah.
And there is a plot where you show the age distribution, but there is also a clump of old and alpha core stars in one of your plots.
Old alpha core in the age alpha relation, you mean?
Yeah.
Yes, this one. Yeah, I think I have a backup slide on this. I need to find it. So yes, these stars, you mean? Yeah. These kind of stars are found also in other works and in the age alpha relation. And I don't know really what are these stars, but two possible explanations would be that they are undetected binaries, and they are found in this region, or that there are really systematics between the stellar models and the data that lead us to date these stars as old, let's say.
Could they be accreted stars?
I checked in the sample for accreted stars, but I don't think so. I'm not confident that we have accreted stars in this sample. Also because the statistics was low, so I couldn't be able to really have a final remark on this, but yeah.
I have another one. So you have this, you divide the galactic disk in three parts: the inner part, the solar part, and the outer part, and they seem to have experienced different chemical evolutions and whatever. So I was starting to think about the nature of the thick disk and the thin disk. I mean, so they have. How should we think about these components in the end? I mean, is the thick disk an inner disk and the thin disk is? How do we, if we want to identify thin and thick disk stars throughout the galaxy, can we do that, or are there three components instead of two, or how should we?
Well, this is interesting to answer, and well, I think that first of all, the intermediate region, like let's say, is depending on the evolution, let's say, of the inner and the outer disk, because we see that we can arrive at metallicity above solar at 8 giga-year, and then we have this decrease from a gas that is in the outer disk. I think that we have still, let's say, we have a clear component in the thick disk in the inner regions that pollutes the local regions. But we also have the component of the inner thick disk that is present and can be reproduced by a simple, let's say, model like this one. And I don't really know if this answers questions.
I'm starting to, I think, confuse myself a little bit as well.
Okay.
To think about the thin and thick disk. I mean, what are they really? I mean, if we, it seems, I mean, from your plots and also from elsewhere, where I read that age, it seems to be just a kind of age separation between the two. But
yeah.
I mean, ages are, so if we disregard these Astro N and ages, I mean, ages are rarely available and so if we want to study thin and thick disk stars elsewhere in the galaxy, how would we do it? I mean, we're overlapping in metallicities, in kinematics, and what would you say is the best way to try to do it if we had a sample like Gaia with the RV sample in Gaia?
Yeah, I think our let's say main efforts should be put on ages of the stars, because really they suffer of large uncertainties, especially in the oldest stars. So to characterize the thick disk components and to really understand if there is like a clear transition between two these components, if they are the same component or if they are really separated. I think we need more accurate ages that really have in this, I think.
But then at the same time, we have these blue stragglers that are affecting the ages and all the chemistry.
Offshore also binary evolution needs to take into account in the models and in the results offshore, for sure.
So you also showed a slide somewhere where you showed the disk profiles of external galaxies in other galaxies.
Yes.
Where we do this distinguishment between thin and thick disks based on morphology, right?
Yeah.
Which is not really comparable to what we do here in the galaxy.
Yeah. Well, I think about morphology, it was, I think, what was done the first, let's say, first works that wanted to characterize like really with star counts from the galactic midplane, but we need also to have the other properties, because I think that just only for morphology is not enough to do that, for sure. We need like a more global view.
Yeah, no, because the scale heights and scalings are not in agreement at all, but both the morphological and the chemical classifications of the thick disk, for instance, and the thick and the thin disk. So, you want to continue?
Of course.
Thank you. That's all. Follow up.
Yeah, thanks a lot.
Go ahead. Yes. Yeah, Valeria, thank you very much for the presentation and the thesis. It was a pleasure to read. Found it very interesting. And so, as when you read interesting things, you have a long list of questions. So,
Okay.
just ask a few. As you mentioned, you rely quite a lot on astron and ages.
Yeah.
Can you elaborate a little bit more about what are their limitations?
Yes. Yes, the main limitation of Australian ages, as also they are seeing in the main paper of the author that is accurate 2018, is that they underestimate the ages of stars older than 9-10 gigayears. So they could be also of about 3 gigayears. So they could be older, and this is the main limitation. Also about the concerning the thick disk characteristics also, and yeah. In addition, I think also another one main limitation would be that they say that possibly ages are wrong for really metal poor stars, but we don't have really metal poor stars in our sample, so we went ahead with the astronomy.
In terms of what's the, I guess, underlying physical reason why one can potentially say something about the age of these stars, can you, as you also mentioned in the thesis, they are calibrated on some catalog based on seismic inferences, but then how come that one can just using a spectrum, a light spectrum, get an age?
Yeah, yeah, because yes, I also have a slide on this if you need a second, I think. Sorry, I don't remember where it is, but I had this slide. Well, showing that basically astronomy is relying on, in particular, to the CN ratio of stars. So this ratio is really vary in the stellar interiors to the CNO cycles, and then this variation of the internal elements CN is like brought up to the surface during the first dredge up that is happening at the base of the red giant branch in the evolution, and so it detects like this variation of the CN ratio is related to the mass of the stars, and in particular higher is the variation of this race. The variation of this ratio is higher the mass of the stars, and then they calibrate a relation between the mass of the stars and the age of the stars. This is what they have done.
So there is some dependence on how well we understand also mixing with stars.
For sure, yes, it's really depends on the model of the stellar interiors, for sure, yes.
Thanks. Then still on the young alpha rich, which at some point we should call them something else because we don't believe they're young alpha rich.
Yeah.
You're focusing at least initially on looking at their occurrence rates at low log G, right? Or relatively low log G, so I don't know, less than 2.2 or something like that.
Yeah.
Then you also looked at the blue stragglers from the main sequence.
Yes.
Can you see any changes in the occurrence rate of these objects in different evolutionary phases. Is that, and if yes, is it potentially telling us something about their origin as well?
You mean the variation of the rate in, for example, Brooks treasures in respect to the sick disk? Yes, I don't have the number in mind yet, but I remember that that we checked in some results of open clusters, for example, and we saw that our number of younger bridge stars, so not blue stragglers, the really giant young bridge stars, it was the ratio was lower in respect to the sick disk reference population to the ratio that people found in open cluster, and this could be explained because of course the number of the stars is really need to be, let's say, it's not really an absolute number. It really depends on how you do the selection and the selection of the thick disk, of the chemistry, the chemical scale that you use. So this was the result, but you need to be careful when you look at these numbers.
And within the samples you looked at, so the fractions here of blue stragglers,
yeah.
Is it comparable to the fraction of young alpha rich in the upper RGB, or just out of curiosity? I'm saying that because in some of the samples, or in Kepler, we could see a higher fraction in the core helium burning phase as opposed to the lower RGB, and one could say, well, there's going to be interaction between those objects. It's more likely that it happens when the stars become large, and so one potentially can learn something. But I don't know if you had a look.
No, I actually didn't look at that, but it's really interesting, and it could be a follow-up for sure, this work.
Another question on the perhaps on the uncertainties on the age. I think you mentioned that in the slides as well, that we've taken a sort of threshold in the uncertainty. I don't know if it was maybe 3 gigayears for the young alpha region, and looking at what happens when you have 1.5 gigayears, etc. The question is, why take a threshold which is at, say, absolute in gigayear and not a fraction of the age? You know, one could say I take ages that are, you know, is lower than 20%. Because then I think you described that in the thesis as well, but all stars, of course, they tend to have larger uncertainties in gigayears, so you might introduce a bias in your sample if you just set a threshold, an absolute threshold. So I was wondering if that makes sense.
Yeah, that's not really a reason why we choose to use absolute value for the cutting edge error. But yes, this is another thing that I wanted to do actually, was to see if there are significant change in the results if we use a relative, let's say, error to cut the sample.
If I may stop me at some. In terms of the, I think you mentioned that I guess when you're determining ages for main sequence, say turn-off stars, when you look at young ages, in your, I don't know if it's the posterior or the PDFs you have, but anyway, they look noisier. Can you have an explanation why that's the case? Or that,
sorry, can you repeat? Because
I think when you mentioned in the thesis that when you look at younger stars, say a gigayear or so, then those look noisier, or the ages are
like the PDF of the stars was not really very clean, with a clean peak and very thin, let's say, in the wind. I think this is because also in the models that describe the age of the stars in the isochrons at younger ages, I think it was a matter of oscillations in the models, in the sense that the step between an isochron with a certain age and another was really not really small, let's say, and so how the code dated the stars was doing a little back and forward to the model, producing this kind of oscillations. But it seems that despite these oscillations in the PDF, the peak was actually nicely found But it was just to be careful in the age error, because it seems like the age error of the stars is really small, but I think it's just because of the characteristic of the PDF.
Such a specific star here. I think you had a plot in the slides, or maybe in the backup slide, the comparison you made with the paper by, I think, by Valeria Cerqui, where you had ages from your sample and this.
Yeah, the ages, yes, I have it. I have to find it. But I have it.
The question was about this in Valeria's sample. There was sort of, they described, you know, this age and also the yttrium over magnesium, showing that it's a wonderful clock somehow. But then there was a system which is a binary system, zeta reticuli, I think,
yeah,
where they were getting different ages for those stars. But it seemed in your results that you're actually getting the same age. So I was wondering.
I don't think the same age, because I think if I remember that in the one-to-one, let's say, relation that we obtained between age, my age and the age from Nissen, these two binary stars were really off to the one-to-one relation.
Yes, but yeah, maybe I'm wrong, but I thought they were off in a way that would that you would get this. Yeah, see.
Yeah, these two.
Yeah, then it seems that you get the same age, right? I'm reading this one correct. I mean, it's compatible, right?
Yeah.
While in Nissen and Tal, they were getting ages which were, I don't know, maybe slightly off. I was just wondering what changed. Why is it the same data that you used, or?
Oh, well, I don't know if this answers your question, but yes, I did the data from Nissen 2022, so it was about 72 stars, solar vicinity stars, with the same exact isochronism method that I used for the rest of the sample. So I'm not really sure what to conclude on this, but yeah. Maybe a better look on what they say about this peculiar star.
Last question.
Yeah.
On the I guess going back to Thomas's question on those old alpha poor stars.
Yes.
And somewhat connected to the discussion you have about the age velocity dispersion relation.
Yeah.
Right, that you don't really see any substantial sort of difference in the behavior between the low alpha and the alpha, just a continuous.
Yeah, I have also a slide on this, I'm sorry, but yes, this one now.
Yeah.
Yeah.
So I was wondering, those stars that, at least in the plots, look like very old alpha poor stars. If you included them, so you would have high alpha and low alpha stars, or some of them at the same age, whether the velocity dispersion in that case would show a significant difference, perhaps, or not. And this you know, the low alpha, very old stars, some may not like them. Other people, it's very fashionable now to say, oh, this is the local evidence for the very early formation of the thick disk, as we see with James Webb. So there's a lot of possible explanations. So I'm just wondering, or just saying, maybe don't just throw them away, because they're quite
they need further investigation, of course. It's another follow-up.
As you mentioned, also in terms of binarity, you focused on stars that accrete mass, but there are cases where stars are sort of partially stripped of their mass, and then they appear older. So
yes, it's true.
They're very interesting.
Yes.
Okay.
Thanks.
Hi, Valeria. Thank you very much for this very nice presentation, very clear, and the manuscript also very nice. It was very pleasant to read. I have obviously a bunch of questions, and some of them were already asked, especially from Andrea, regarding the threshold to have age uncertainty, so I will not come back to that. And I believe that maybe, I mean, that will bias to some extent the dispersion on the ages by having on all ages by having such an absolute threshold rather than a relative uncertainty threshold. But that's something that perhaps you can investigate.
Yeah, sure.
And so I have lots of questions regarding methods and uncertainties, and
Yes.
a bit after about interpretation. And I am agnostic of all of those questions, so feel free to answer the way you want. First of all, yeah, you only briefly mentioned when you compute ages that you don't take uncertainty on extinction.
Yeah.
Can you comment a bit on that? How could you estimate it? And how do you have a feeling of how much it can affect your results and how big it is? Right?
Yeah.
Roughly speaking.
Yes. Yes. Okay. So yes, we don't take it into account simply because the map that I was using didn't provide any uncertainties on that, and also the way we computed it was from the map. It was really difficult to have a value taken into account really, but it's true that the stars that I'm using here are really most of them within 1.5 kbc from the sun. So for sure, if you don't take into account at all extinction, can really affect the position of the stars in a HR diagram and so really affect the age. But in this case, I don't think that uncertainties on the extinction is the real main, let's say, ingredient here to enlarge or enlarge the error of the ages.
Because the extinction map, the Lallemont map, is a 3D map, right?
Yes.
And so I guess you have uncertainties on the position of the star.
Yes.
So one could foresee maybe doing a Monte Carlo on the position of the stars and see how much the extinction changes.
Okay.
I was thinking something like that.
Yes.
But I guess because this is a local sample, maybe the parallaxes are very well.
Yeah, exactly. Exactly. Yes.
Not how much room to increase this uncertainty.
Yes.
The second question, since we're here, is that this Gaussian about the age uncertainty.
Mm-hmm.
So obviously, when you are at the edge of the age range, so let's take young, this Gaussian is truncated, right? You cannot go younger than 0.
Yeah.
And so, how do you estimate the uncertainty in that case? So is the same one?
Yeah, we took the let's say the same sigma that was for the let's say h plus 1 sigma. We utilize that sigma also for the h minus 1 sigma. I don't know if I'm clear, but we take the same uncertainties that we have.
So you feed the PDF actually, right? And then you measure the sigma from the fitting, or how do you measure?
Yeah, so we have our PDF. The age is the maximum, the age that corresponds to the maximum of the PDF, while the h minus 1 sigma and h plus 1 sigma are the age corresponding where the PDF is equal to 0.6. So then we can have the minus 1 sigma and plus 1 sigma uncertainty.
Thank you.
Yes.
Let me go through the questions I have here in mind. Again, still on the ages part to understand a bit, because this is part of interesting part in future surveys and reliable data. So the aids are as reliable as the input parameters that you're using. And if they give wrong TF looks or color, then the ages are wrong also. Presumably also, the reliability of your ages depend on how reliable is the uncertainty in the input parameters.
Yes, yes.
And from past experience of mine, apogee uncertainties are underestimated. Was that taken into account in the way you were projecting our isotopes to get ages?
Well, in a certain sense, in the sense that, for example, we did some tests on the input parameters that we wanted to use for the main results of the work, let's say. And for example, we saw that when we utilize, for example, instead of column effective temperature, the relation then that we obtained in age alpha was really more dispersed, more spatial. So, and also we know that there were some problems also with effective temperatures of apogee that, and so we decided also for this to rely on the more precise peak color, even though there is the extinction now also problem that affects the magnitudes, but we decided to do that.
And what about metallicity then?
Yeah. Well, for sure, there's a number of things that are underestimated into the calculus of the age uncertainties, and one of them is for sure this. But because we know that the metallicity errors are underestimated, like formal in apogee, so for sure would be this. What I show is like formal errors. Let's say there's a number of things that are not taken into account, like this one, for example.
That's enough about the methods and the things. A bit about interpretation now. So slide 20, you show a tumor diagram.
Yeah.
With your young alpha stars. Yes, that one. And so I don't think you mentioned it during your presentation, but in your thesis you talk about the possibility of some of them being acritic stars, or yeah. And so I think you conclude that acritics, you shouldn't have many young alpha rich stars among the acritic stars. Here I see some retrograde stars that are young alpha rich. Very naively, I would think that retrograde stars are acritic stars. So can you comment a bit on that? What are maybe the other mechanisms that can create retrograde stars if it's not unusual?
Well, I honestly, I'm not sure how to answer these questions, but starting to say that, yes, our results really are not very conclusive in respect to acritic stars, because yes, we selected possible acritic stars in energy and so on, but there are really small sample to really say something about that. So I'm not really sure how to answer these questions about the possible mechanisms that can produce retrograde stars if not that.
Right. How much time do you have more? Do I have one or two questions?
Oh, yeah.
Yeah. So I'm sure you're aware that some works claim that the bar is young.
Yeah.
Your results overall, your conclusion seems to favor an old bar. Can you put your results into perspective with those people claim that the bar is young, and then just your comment on that?
Yes. So as I said, in the simulation that we have, the bar stopped, let's say, to slow down and at 1-2 gigayear after the formation. And since we think that the bars slow down induces radial migration of the stars that are rich, and we see these signatures really in all the stars of our sample, in particular in apogee 5-7 gigayear, but we also take into account that there could be, as I said before, these ages could be underestimated. So let's say of about 1, 2, 3 a year. Given that the bars stop to slow down 1-2 gigayear, we really said, okay, this is the signature of the fact that the bar is old as 10 gigayear. Otherwise, we should have seen maybe these features in younger stars as well, and not only in old stars, but we really do see this in all old stars. Also, when we look at the metallicity profile, sliced by age that I'll show, I think, in the thesis. We really see that the bars, this step is really appearing as stars older than 5-6 gigayear, but it's really stronger in the stars that older than this, but in younger ages we don't see that. So this is my conclusion, let's say.
Thank you. And my last question. So let's suppose that you are the richest person on earth. You have an unlimited amount of money, unlimited amount of time. You can hire whoever you want, build whatever telescope you want to use tomorrow. What would be the first thing you would do tomorrow? There's no wrong answer, so go ahead.
Okay. Yes, well, I think naively, let's say, I would really invest in some surveys that would really give some precise measurements of the chemistry in all the regions of the galaxy, and in particular, maybe that can have the most of the stars also in common with other previous surveys to really understand all the systematics that we also see between surveys, because it's really difficult to use magari some of them together because they derive chemistry and so on in different ways. And also so to really see also another thing that could be is really something that can unify, let's say, the pattern or whatever to find the same scale on chemistry in between the different type of stars, and to also enlarge even more the sample of stars that we can study. And for sure, also we need to put effort in determining stellar ages, particularly for all the stars. This is what I would say. Thanks.
Thank you, Jean. So now we take the question from Céline online.
Yes. Yeah.
Please.
You can hear me?
Yes.
First of all, I want to apologize not to be with you. I was not able to travel yesterday, and I was afraid not to be early enough on the top of the hill today. So sorry about that.
Yeah.
I wanted to congratulate you for your manuscript, which was very nice to read, and many important results on the Milky Way history. And also your presentation was very clear and very good summary of everything you did in this study.
Thanks.
I have a few questions. So first one is on your slide 28.
28.
Yes, where you show here a separation of your dwarf and giants in this
Yes.
FG histogram. I was wondering what when you cut at 4.45 and what is the peak at? It seems there is a large sharp steep after this. Is the artifact, so why don't you use that?
This peak after 4.45, you
Yes.
mean?
Yes.
Yeah. These stars actually rely on the binary sequence in the lower part of the main sequence, and so we prefer to discard that. And it was really also nice to be able to discard most of the binary stars, let's say, also from the log G here. It was really separated. But of course, we expect some contamination because it's not really made by eye, and but yes, this is for what was the reason.
Okay. Also, you didn't show it here, but your next plot in the thesis is alpha F versus age for this dwarf star. but I understood that the ages here are not correct for dwarf stars because it's based on C over N. So I guess you show this plot just as an illustration.
Yeah, exactly. Yes, to give the impression that even though, yes, Astro and N ages are not meant, let's say, for dwarfs because it utilizes this ratio that varies in giant stars, we really find the young alpha-rich stars, blue straggler stars, in the position, exact position where other works find the blue straggler stars in globular clusters. And so whatever the age, also if their age is wrong, with our selection, we are able to find these stars and that we know that locates here in globular clusters very well. And yeah, just to show that.
Okay. And on the age determination from the C over N ratio,
Yes.
it has been shown that it's from evolutionary models that this ratio can strongly vary in the model depending on the mixing process included, like rotation, thermoline. Do you know how this can change your conclusion, or depending on what mixing is taking into account in the evolutionary model? Can it change the age a lot from the C over N, and how would that change your level?
Yeah, yes, this is one maybe the main issues that we can have on this, because of course it can. I think I don't remember really well now, but I think there are some papers maybe from Montalban in the literature that shows that CN can really maybe depend on the mix of the stars, or let's say some processes that happen in the stars. That I really don't remember it very well now, and not sure how to answer your question. But anyway, we see that the results are then consistent with the ages, but it's for sure something that can be investigated more to validate the results for sure.
I had a question about the migration. With Gaia, we see actually in the solar neighborhood that stars in the solar neighborhoods today comes from center part of the Milky Way. So they have a apoapsis very close to the sun, but periapsis very close to the galactic center. How this can be disentangled from radial migration? Do you know if there are many of the stars, and if this orbital has to be taken into account?
Sorry, can you repeat? Because
So
I think
when you talk about radial migration, so the idea is to see if stars are coming from the center of the galaxy, have been formed close to the center of the galaxy and migrated close to the sun now. But there are also stars in the solar neighborhood that we know of orbit that they are coming close from the galactic center. So they are not migrated, they are just
okay.
in orbit, and they are now close to the sun.
Yeah, indeed. This is why we used the guiding radius intervals instead of the intervals in the actual radius of the orbit, because the guiding radius really can trace really the birth radii of the stars instead of really the radius of the orbits in which the star is now. So this is really results that we should be to show the stars representatives of the different regions, and not on the orbits of the stars. It's like a mean radius indeed. It's not the radius of the actual location of the star.
Okay. I had another question on your chapter 4, when you show the absolute magnitude versus TF or versus color. of your sample of apogee data, it seems that you have Ngala. It seems that you have some sharp cut at magnitude 3.5 in K and 5 in J. And I was wondering, is that because there is no apogee Ngala for the main stars? And also, it seems that you are trying to get a sample of dwarf star, but it seems from the plots that you also have evolved stars in the population.
Sorry, I didn't understand you. Can you repeat? Sorry.
Yes, in your chapter 4, you are making a sample of dwarf stars. And when you show your selection,
Yes.
your plot, which is 4.1, I don't think you showed it in your presentation, but it seems that you don't have only dwarf stars, but also evolved stars in your plot.
It's
after the turn-off.
Sorry, I don't hear you very well.
If it's in page, okay, maybe this one. Yes, this one.
Yeah, this one.
Yes. So I was. They are not all in the main sequence, right? You have on the right, they are evolved stars.
Yeah, they are also in the subgiants branch.
Okay.
And yeah, because also stellar models are really, I think, so we didn't really go down in the main sequence stars because this is the region also where the isochrones mostly overlap, and so we could have more uncertainties or possibly wrong gauges on that. The models really separate a more distinct way, let's say, into the region of the main sequence turn-off. So we selected these regions, let's say, from the subgiant branch to a certain limit of course, of, let's say, main sequence stars for this region.
Okay. Okay.
Thanks.
Okay, my last question was about the Nissan age, but Andrea already asked you. That's all for me. Thank you.
Thanks.
So, thank you, Céline. Misha, maybe I ask a question before giving you the floor. I don't know.
I don't have a question, so you can.
So, yeah. So thank you very much, Valeria. I really appreciated to read your manuscript. It was very clear for me, who is not a specialist of the domain, and also your presentation, which was also very clear. So as I followed you for 3 years, because I was a member of your committee, the suivi individuel, I have not so many questions. However, I have a question about the chemical evolution model.
Yeah.
You mentioned this model by Snaith and Paul. Yes.
Yes.
And you use it, you modify things. Is it a code which is available? What is the form of this? What is
it? Sorry.
What is it, this chemical evolution model?
Yeah.
Did you calculate something?
Yeah, actually, we used the calculation, the model was built originally in 2015 and with some modification in 2022. But I think for the linear disk, we really fit this model in the data, in the sense that, as I said, the alpha over error ratio depends on the star. Its variation with time depends from the level of star formation in that time. So we used the star formation level as a free parameter, let's say, to be able in the model to be able to fit the data in an iterative way, so that we can end with a model that fit the data, and also on the other side we can end with a star formation history as a product of this fit.
Okay, thank you. I had also a question about the bar. I don't
Yes.
know anything. I remember, but maybe it's completely wrong, having seen some theoretical simulations of the bar by Bourneau, something like that, showing that it was a transient structure, appearing, disappearing, etc.
Okay.
How does it fit with what you do?
Okay, so honestly, I don't know the paper that you were citing, but we really do see in the structure, also in the morphology of the central part of the galaxy, that where there is the badge, and the badge is dominated really by this triaxial bar structure that gives a sort of peanut, we say peanut box shape, and this is a really feature also from what we see, but also from what was modeled, for example, in Gera 2015, 13, I think. And, not really sure how to relate this to the fact that, as you said, some simulations so that it's a transient features.
Thank you.
Yes.
Also, you didn't mention it, but I know that originally your thesis should have been based on with data.
Yes.
2 years of
Yes.
data were expected. And well, you mentioned it in the conclusion and perspective, but could you say what you have missed? Because you have so many results anyway.
Yeah.
Maybe a bit
Yes.
about that, comment a bit about that.
Yes, I think that possibly the with data could have give more data, more precise data, also a lot of more stars in the solar neighborhood. So I think would be really helpful also to have chemical. Well, to really define to compare pH chemistry relation with this data, also to have more statistics than what we have, because we do a lot of cathode selection and so on, and having more statistics really also helping into reconstruct the different features, how it relates to time and so on. But it's a bit difficult to say now what I missed, what I should have accomplished with the WIV survey, because in the meanwhile Apogee came and it also doing a good job at the end. So yes, this is my conclusions on that.
Okay, thank you.
Thanks.
Congratulations to have struggled with all that. And finally, a very short comment about, again, the ages and the models. I think really Yale-Yancey isotopes are a bit old.
Okay.
In terms of, even if we do not know yet for sure what is the solar chemical mixture. So there are all things involved, I suppose, and for future work, it would be good to update. It's not
Yes.
it's some work, but
Yeah. Thanks. Yes.
Misha, please.
Sorry, I don't have questions.
So nothing to say.
I was planning to make a comment after the,
Okay.
at the end, but I want to say that Valeria has. I'm happy to see that she has finally been able to present that work, because she has put a huge amount of work in producing the stellar ages, and that was not an easy process. In particular, since what you just mentioned about the fact that we missed the WIV data, and we were really counting on that, and we were still waiting for the WIV data. But,
we hope that someday we'll be able to continue working on this using the data. And she has been, in any case, she has been able to really to take the most of what could be done with the approach, and I'm happy of all the results that she was able to obtain.
Thanks.
And so I have no particular question to ask her because we discussed this a lot previous years. So.
Okay, thank you, Michelle. So before we deliberate, I can ask if someone in the audience with a PhD degree has some question to ask. No, so if not, so I will ask you to go.